All right, we'll go ahead and get started here. Today we'll be exploring SOLIDWORKS Flow Simulation and how to best analyze all-electric designs. My name is Enrique Garcia, and I'm a Senior Applications Engineer here at GoEngineer, specializing in our simulation products. And this will be part two of a three-part presentation series that will explore various capabilities of SOLIDWORKS Flow Simulation. Before we review the agenda for today, here's a general slide showing how SOLIDWORKS Flow Simulation is offered. Again, one will typically purchase SOLIDWORKS Flow Simulation and then specify if you would need any of the two below specialty modules, whether that would be the HVAC module or the electronics cooling module. There will be some tools that we'll be using that are only available in our HVAC or our electronics cooling modules. Please let me know or anyone here at GoEngineer if you have any questions on this. All right, so here's the agenda or roadmap for our webinar series. We'll start our second webinar today by setting up our all-electric design with conditions to investigate how our design will perform when left outside in direct sunlight in the hottest place on Earth. Then for our last webinar, we'll keep refining our setup and flow simulation in those extreme conditions and begin to use some of the more specialized tools available in the electronics cooling module and take another look at the accuracy of our design. We'll also introduce some tools that can help with a more accurate thermal power output for your analysis. And just as before, in case something comes up or if you have to leave the session early, we'll be recording this webinar and we'll be posting it onto our GoEngineer YouTube channel after a few days. If you have any questions while I'm presenting, feel free to ask. And if there's no glitches on my end, I'll be able to see your questions and answer them as I go along. Also, as always, we'll have some dedicated time at the end of the presentation for questions. All right, so last week we set up our simple electronics box in SOLIDWORKS Flow Simulation with our standard and general conditions, right? Then we confirmed that our temperatures of our integrated circuits under the two heat sinks did not go beyond the operational limit temperature of 95 degrees Celsius. So that's what we did in a nutshell last week. So for our next section here, we're going to be changing the ambient conditions of our project to see how our components respond thermally when operating in the hottest place on Earth. Can anyone guess here what that's going to be? Feel free to use that chat or the question interface to respond, whichever one is available to us here. Take a moment. The Sahara Desert. Yeah, that's a good try. I would think the same thing, but that didn't come up actually, but good try. Anybody else? Egypt. Yeah, I guess, yeah, Egypt, like where maybe Cairo or something. That's close to the equator. Yeah, that's about the same. Yeah, I thought that's a good guess as well. But actually, let's take a look. And so the hottest place on Earth was measured in a place called Furnace Creek, which is a small town in a place called Death Valley in California. So Furnace Creek only has a population of about 136 people. The record temperature was recorded in 1913 with an air temperature reading a sweltering 134.1 degrees Fahrenheit or 56.7 degrees Celsius. There are other ways in which we can record temperature readings at locations around the world, like ground and satellite readings. However, we go with air measurements as a standard measurement type because of unreliable ground and satellite readings. If this record is ever decertified, then the record would go to a tie for a temperature of 129.2 degrees Fahrenheit, which would be once again a tie between Furnace Creek in Death Valley and also Kuwait. So a little bit of knowledge there for you. So let's go back over to our SOLIDWORKS screen and let's set up this project with these new conditions. All right, so the first thing we're going to do here is we're going to set up a new flow simulation project. We're going to come over to the flow simulation tab and once again use our wizard that we've become familiar with. Let's give this thing a project name. We'll call this one maybe part 2. We're going to use this current configuration there. And this will be a little bit of a rehash from last week, but we're going to be choosing for our units, SI units, Our temperature, we're going to change to Celsius here. For our analysis type, we're going to be switching it over to internal analysis. And we're going to make sure that conduction is turned on here under physical features. And we'll turn on radiation. Next, down below, before we forget, let's turn on gravity. And let's change the component of gravity, again, back over to the y direction and zero out the z component of gravity there. We're going to make sure that our arrow is pointing in the appropriate direction. That's in line with the y direction. And let's come on back up to the radiation model. For the radiation model, we're going to be leaving it at discrete transfer here. And down below under the environment temperature, we're going to be changing this from room temperature over to our 56 degrees Celsius, which will emulate what we have on the hottest place on Earth in Death Valley. So again, this is 56 degrees C or about 134 degrees Fahrenheit. Very toasty. Also, because we're going to be turning on solar radiation here as well. So let's pop on solar radiation. We can start seeing the symbol there to the right-hand side of the screen in the graphics area. And we're going to specify this by location and time. So let's switch that up. For the location, we have a couple of options for this. I can hit the pull down. I can choose from some of the more popular locations on Earth, or beforehand, I've added a location in the engineering database for Death Valley, Furnace Creek. So we'll go ahead and choose that location. And again, it puts in my location in the engineering database, basically. We can set that information beforehand. Now, I want this to be as toasty as possible, so I want to go in and pick a date. So a good date could be maybe July 4th. So let's update that with July 4th. And around the time, let's say high noon is fine. I think that's going to be perfect for that. So a little bit about solar radiation. So this enables directional radiation from around the ambient space. So we don't know if radiation and solar radiation will play a big role here in this heat transfer in the areas we care about, but this is how we would set it up. So we won't know unless we try it, right? So we'll try it here, and maybe we'll try it without it later in another version of this project to kind of test that theory. So let's continue on, and let's specify the default fluid medium, which is going to be air under gases. Let's click next and specify our default insulator there as we did last week. And default wall conditions here as well. Notice that we have additional radiative surface default conditions here. Let's click next. And for our initial conditions, we're going to be changing, very importantly, the temperature there from room temperature over to our toasty 56 degrees Celsius. Let's click Finish to create the project. Now, the rest of the setup is very, very similar to what we've been working with so far. So in an effort to help alleviate some of the redundancies, I'm going to continue with part 2 completed here. And let's step through this setup here that we already completed last week. The first thing here that we can notice is we've assigned the materials to all those same components. Just as a review of what we've done so far, we set up a stainless steel 321 material for the plates there of the housing. We've chosen copper for the 2 larger transformer components. We've selected silicon for the 6 square PSUs there, the round capacitors, and the parts that make up the 2 integrated circuit packages under those 2 heat sinks. Moving on, we've selected for our aluminum, we've selected the heat sinks as well for those, the very large capacitor there to the far right, and the 4 medium cylindrical capacitors. And lastly, for the PCB, 4-layer PCB here, we selected that here as well with that with the anisotropy direction of the Y direction. So that takes care of assigning our materials to all the components. The next thing, if we remember, we assigned an environment pressure condition to the two interfaces of those lids covering the vents for our electronics box. Next, to be able to drive this forced convection behavior, we set up an external outlet fan, and we've chosen the inside face there of that housing area. We told it to choose external outlet fan, and then we picked a custom BAPS DC axial fan. Now again, this is something that I popped in manually, but if you had the electronics cooling package, you have a full extensive list of all the different types of fans available here that come with that module if you do decide to purchase that. All right, let's close this out. So far, all review from last week. The next step would be to assign the heat sources or heat energy sources for our entire system to all, or at least for us, the major key components that participate in heat generation in our system. So as a review, we set up our heat generation rate for this first IC there of 2.5 watts. We did the same for the other instance on the other side on the far end there. Then for the large capacitor, we set up 10 watts. For the four smaller capacitors or the medium capacitors, we set up a total of 5 watts for that particular set. And lastly, for the two large transformers, we had a total of 4 watts for both of those transformers. Now the last thing to do would be to go in and assign an engineering goal. Like we learned last week, we need something to converge on. In this case, we're still converging on those very important and sensitive IC packages here for our system. So at that point, we went ahead and we ran the analysis, and I've already preloaded the results here for a review. So the first thing I want to do is look at my goal plot for this particular project. So let's jump in and edit the definition of that. Ensure that we're going to be showing the goal plots for the two solid ICs. And let's take a look here, and we can see some stuff here. We can see that the goal plot shows temperatures for the ICs at about 104 and about 97 degrees Celsius. So our design is definitely surpassing that operational limit temperature of 95 degrees Celsius for both of these ICs, just for this climate, right? So that's initially here what's going on. So not much more to see in that sense. Everything else is the same. We've just been changing those. We added radiation, and we changed the ambient initial conditions there to very hot and toasty 56 degrees Celsius, or I think that was 134 degrees Fahrenheit. Super hot. So let's see what happens if we add an extra fan to the model and see if the additional cooling can help. So one of the nice things with flow simulation is that we are in the SOLIDWORKS ecosystem, and we can easily go and just switch configurations and copy projects or clone projects and apply the same constraints over with minimal effort. So the idea for this is I can take this model here and I can clone this project, and I can add it to the two fan configuration for this. So I'm going to go ahead and do that right now. I'll go on over to the top of the flow simulation design tree and select clone. And I can give it a name here. Maybe I'll call this one part 2 underscore 2 fans to keep that straight. Now, very importantly, we choose the different configuration. This is going to be the one that has 2 fans and this similar heatsink design. So again, we're copying and harvesting all of that setup over to this new project. And the only thing we're changing now is we have that extra geometry, and we can add a second fan definition. So I can go and say insert fan, choose external outlet fan like before. This time I'm choosing that interface there. We do have that extra blade there. That's not going to be participating in the calculation here. So we can suppress it, or we can just ignore it, to be honest. And down below, I'm going to choose my same fan, my custom fan that I've selected and added in there. Click OK. Now at this point, I could run the project, or in my case, I'm just going to go ahead and open up the part two fans completed version of this. So let's activate that particular configuration, and we'll roll through those result files. So let's come on down, and again, let's take a look at the results for this model that we set up with two fans instead of the one. We're hoping we're going to get some sort of cooling, right? So let's jump over to the goals and take a look. So our official results have improved. So the maximum temperatures for the ICs are a bit lower at 92 degrees and 97 degrees Celsius. So again, we get a bit of an improvement, but one IC is most likely will still fail. There still may need to be some underclocking or power regulation in this case to help out with the extreme climate. Let's close this out. So let's take a step back and look at the bigger picture here. So we've been running these projects by calculating the internal volume of the box and idealizing the external environment so far. So let's see what happens if we introduce a bit of actual air fluid medium around the box. So we've been assuming that most of the heat transfer happens by the air entering the two vents and out of the fan definition regions, right? So, but now let's see let's go ahead and explore if the natural convection of the actual electronics housing can help with the heat transfer in those IC areas. So for this, we're going to clone this particular project, and we're just going to switch the analysis type over to external analysis. So let's go ahead and do that again. So the workflow is just going to be to right click here, or I could also just right click on the highlighted project in the project manager and select clone. And we can give it a name here. We can call it external, maybe part 2, because this is our second webinar with 2 fans, and the current configuration is perfect. There it is. Now at this point, we would go in and let's edit the at this point, let's go ahead and edit the general settings. And we're simply going to change the analysis type there from internal back over to external. Click apply and close. It says that the geometry has been modified. Do you want to reset the computational domain? Absolutely. I want that thing to grow out and get some of my additional volume of my air fluid medium on the outside. So let's click on yes. So now let's take a look at our computational domain. Let's go in and edit that here. You'll notice that it's quite large. And just to save on calculation time, we can choose to shrink this volume here. At least for maybe a preliminary study, just know that shrinking it too much could affect how your flow fields surrounding the geometry of the box, which could throw off your overall result. So just be a little careful about doing that. But you can maybe shrink that up a little bit just to help with your calculation. All right, the next thing to do is maybe apply some additional material to the components here. We can go in and assign additional stainless steel to the top and bottom of these components. But in fact, and we're going to be running the project. So let's go ahead and open up the already run project, because once again, especially with an external analysis, we have a lot of we have a lot larger of a volume to calculate. These definitely take upwards to over 5 minutes to run easily, even with this preliminary mesh detail that we have on the model. So let's go in and open up the already completed project there. We'll open up the external part 2 project there that's been completed with the results. Again, with the 2 fans. So let's take a look here let's make sure it's been loaded. Looks good. And let's take a look at our goal plots. That's what is going to be most important for what we're looking at here. So let's look at those goal plots. Let's see if we had any change in the results. Yeah, it looks good. So temperatures are now 90 degrees for one of the ICs and about 96 for the other. So yeah, there's a noticeable difference between the internal only and the external project that we've been experimenting with. So we can probably all agree that even though these projects are preliminary in nature, like I've been mentioning, this setup is a bit more accurate. So we'll keep setting up using an external analysis moving forward. Let's close this out, and let's show some cut plots of the outer air fluid medium here, just around the electronics box. Let's pop those on here. And let's maybe turn on the surface plot so we can look at the outer surface of the box here as well. Looks good. Let's get this out of the way. All right, so we can see here that we have some heat transfer due to natural convection, and we can see that the direction vectors of the fluid medium here are pointing upward. So we're showing the direction of the air fields here. But we can probably conclude based off of the temperature differential that the majority of the heat transfer is being driven via the fans due to only a slight temperature difference, at least in the ICs, right? Based off of the previous project. And I guess overall, the natural convection of the outer housing is not playing a big part in the heat transfer, again, around those components of interest. But it is definitely playing a role here, as we can see, in maybe potentially other components, but it is playing a role, and every little bit of accuracy helps. All right, so that was our second setup for this series. In our next and last webinar tomorrow, we'll continue to refine the accuracy of our setup and thermal output in our project. So we'll review some specialized features that come as a part of the electronics cooling module, and we'll explore those capabilities. Before we end with any questions, I just wanted to promote our dedicated GoEngineer YouTube channel. We post videos here very regularly and invite you all to subscribe and stay up to date with our latest uploads. We also have a wide range of topics that are covered, including simulation. So definitely feel free to stop in and check out what we have. Once again, we also produce a blog on our website that's very active with many tips and articles with useful information. Topics that are covered are SOLIDWORKS, simulation, many other technical topics, as well as fun projects our engineers have been doing with 3D printing and scanning. All right. With that being said, I'll stay on for a few minutes here once again and help answer any questions you may have. So again, thank you for attending our presentation today, and we'll see you on the next one.